Use Newton's law of cooling for the following example. An object is heated to 75 degrees Celsius and then it's allowed to cool in a room whose air temperature is 30 degrees. In Newton's law of cooling, the capital T is going to be the variable that represents the temperature of the surrounding medium, which essentially is the room's temperature. And in this case, cap T is 30 degrees Celsius, so we'll just be using 30 in our formula. U naught, or U sub 0, is the initial temperature of the object, and so we'll be using 75 to plug in for U naught in our formula. Our Newton's law of cooling formula is another exponential function, and as we've seen before, the first thing that we're going to need to do is use these initial conditions to find the value of K, which is describing how fast the object is cooling down. So the first thing that we need to do is use the initial conditions to find the value of K, which is considered our rate. So we start by plugging these quantities into our Newton's law of cooling formula. So we have U evaluated at T is equal to the temperature of the surrounding medium plus initial temperature, 75, minus that cap T quantity of 30, multiplied by e to the KT, but we're going to need some more initial conditions in order to determine the value of K. If we're going to solve for K, it needs to be the only variable in the equation, but we still have T and U. So let's look into part A to see if we get any more information that can be used to find our value of K. We're told that the temperature of the object is 60 degrees after 5 minutes. And this is information that tells us how fast the object is cooling. So we can use this to determine the rate of cooling. So we'll plug 60 in for the output temperature. The room's temperature is still 30. The initial temperature of the object is still 75. We're hoping to be able to solve for K, and we know that it took 5 minutes for the temperature of the object to reach 60 degrees. And now we have an equation that has only this one variable K, so we can solve for it. So in solving for K, we'll notice that the K is located in the exponent position, so that makes this an exponential equation. And to solve for a variable in the exponent equation, we're going to need logarithms. But of course, before we bring in logarithms, we definitely want to simplify this equation as much as possible. So we'll start by saying 30 plus 75 minus 30 is 45, and that's my multiplier on e to the, let's call that 5k power. We continue to simplify. Let's subtract 30 from both sides to get 30 on the left. 45 is the multiplier on e to the 5k power. And we're still trying to isolate the base that's being raised to that variable exponent, so we'll divide both sides by 45. The 45's cancel on the right. We have a factor of 15 that goes into the top and the bottom here. So we end up with e to the 5k is equal to 2/3. Now we're ready to bring in logarithms, and we can do that by either converting to log form, or by taking the log of both sides, but because we have base e, we would say take the ln of both sides. We can do either one of these, but in this example, I'm going to convert to log form. So this is log base e, or ln, which is the shorthand for log base e, of 2/3 is equal to 5k. And now in order to solve for k, we need to just divide both sides by 5. So we're going to get a decimal quantity for our value of k, and then we're going to store that into our calculator. So we have ln of 2/3. Let's get that quantity and then divide it all by 5. And again, we want to use the store button to make sure that we save all these decimals. Essentially, we're saving the exact quantity of our k. I like to store it into x to make it easy to access, and then we'll hit enter. So now the entire decimal quantity has been saved in our calculator. But in our handwritten work, I'm going to round it off to 0.0811, just because this number is easier to write down than the ln of 2/3 divided by 5, which is the actual exact quantity. And then we need to rewrite our formula, or the exponential model, to include the rate that we just found. So now we have our temperature is going to be equal to 30. Again, 75 minus 30 was 45 times e raised to the k that we found was 0.0811, and that's going to then be multiplied by the independent variable t. This is now the completed exponential model that represents the cooling of this object. So we can use this formula to determine when the temperature is going to be 50 degrees. So when we're asked to find when something is happening, essentially that means that we're going to be solving for the time. We know that the temperature output needs to be 50 degrees, and we need to figure out who is the T that makes that happen. So we plug in all of our initial conditions, including our found value of K, and this time the variable that we're solving for is time. And again, let's notice that that T value is in the exponent, which means that this is an exponential equation, and we're going to need logarithms. So we'll simplify as much as possible before we bring them in. We start by subtracting 30 from both sides. So we get 20 on the left is equal to 45 times e raised to this rounded off decimal. Remember, we're going to need to use all the decimals from our calculator when we do our final computation. We're continuing to simplify and isolate that base quantity, so we'll divide both sides by 45. 20 divided by 45 is 0.44, but let's use math and then fract that quantity by just hitting enter to turn it into a simplified fraction. We can see now that they both had a factor of 5, and when we cancel those 5s, we end up with 4 over 9. So we have 4/9 is equal to e to this rounded off decimal times t. This time when we bring in logarithms, remember we could either convert to log form or take the ln of both sides, but this time let's take the ln of both sides to demonstrate that process. We're going to put both sides of this equation into the arguments of the same logarithm in order to gain access to the logarithm's properties, and the one that we are most interested in is the power rule. So what we have now on the left is the ln of 4/9, and on the right we have the exponent of negative 0.0811t now times the ln of e, and the ln of e has a value that is 1. So essentially on the right, that's just multiplied by 1, so we'll just have negative 0.0811t. Remember, we're trying to find how long it's going to take to reach that 50 degrees, which means that we're solving for t. So in order to solve for t, we're going to divide both sides by the quantity negative 0.0811, but when we do this division, we want to use the exact value so that we're not generating a rounding error. And remember, we stored that quantity in our calculator, so we can come back over here now and say the ln of 4/9, and we'll hit enter to get the numerator quantity, and then we'll divide that by what we have stored in x, which was our negative 0.0811 quantity. And we can see then that the t value is exactly equal to 10. Remember that our time was measured in minutes, so those are the units here, and it takes 10 minutes for our object to get to 50 degrees.